So let's start. Any questions from the last week? Okay, then let's proceed to this week. Week 9. So this week was all about PDE solvers.
Excuse me.
Yes,
Ash, actually, whatever the solution we get for the previous assignment, they
hmm
are just giving us the answers.
yes,
And I tried from the codes, like whatever the codes from your side and also from the Sunday's lecture, whatever
yeah.
the codes I tried from there also. And additionally, I make a changes over there and find out the answer. But sometimes my answer is not get match with the given options. Can I get the correct like codes for that in the answers of the assignment?
You want the correct codes. So, like, did it happen this week?
No, actually, it's happen in every week, but theory questions are 50-50%. So
Yeah,
theory question, I don't need anything like that is get covered in the theory part and whatever the books and transcript we have.
yeah.
But regarding that solving question by using
hmm
the Python code, some libraries are get introduced and everything over there.
Yeah.
So for that, I tried your code. Like if we
hmm
say that the sum is same as that of what you ask in the assignment,
Yeah.
and then I tried your code and changed the figures. Like
hmm
somewhere the now in the screen there's a 512, 512, and then we have the 500. So we are
Okay.
changing it, but
Yeah.
whatever the answer we got it is not the correct one, and if we are
Okay.
not getting the answer from any of them. So it is get wrong. I get the
Yeah.
less marks in the assignment. So I need the correct answer of that. So my code has some problem over there.
All right. So one thing, if all of you feel that way, then we can solve from previous week. And if you think only you have problem or you don't want to share which problem, etc., you can write to me and send your code also, and I can verify. So, do you want me to solve any question from the last time?
Yes, 1 minute. I'm just giving you the
Yeah.
number from the last week.
I have it on my screen. If you can see on the screen, week number 8. Yeah, there is one on the wave equation, one on diffusion equation, one on 2D Fourier transform, and one on Parseval's theorem. Which one was it?
Ninth one.
Ninth one. 2D Fourier transform. Okay. So it is okay. The function is given, and you have to find kx Fourier transform at kx ky, right? And it is given to be 2 comma 2, right? This one, right?
Yes, ninth one and also first one. I tried with the like changing in the code two times.
Okay.
and then I got the two, both times I get the different answer. So first when I tried to solve this, I got the answer 0.0625, that is the correct answer. But
Hmm.
later when I changes the things regarding some formula, I thought that there is some issue with the codes and everything. So I find out the answer, so I get the 0.25 in the Jupyter notebook I tried.
Okay. First of all, we can do this analytically, right? Did you try that with pen and paper?
No, no, not at all.
Let's just do it analytically first. Of course, we'll do do it in code also. So this was assignment. Okay. So the function is, this is from new assignment, right? New, I should write the full problem number 9, question 9. Function is 1 plus cos square x cos square y, and we have to find Fourier mode for 2 comma 2. Okay, which means the coefficient of the form e to the power I 2x and e to the power I 2y. So this will be 1 plus cos square x. Cos x is e to the power 2, e to the power ix plus e minus ix by 2, and square e to the power iy plus e to the power minus iy divided by 2 square. Okay, so it will be 1 plus 1 by 4, and the first term itself will be e to the power 2ix and 2iy, which is what we want. Okay, so the Fourier coefficient is 1 by 4.25. That should be the answer. Is it what you got?
Yes.
Okay, but they are saying it should be
Zero
0.0625.
0.0625.
Okay, then I think most likely it's error on their part. Yeah, um, I'd done this actually, and it had matched with the solution. Let me just give me a moment, okay?
Actually, I use your code, then I got the answer 0.0625. But I feel it that not copying the things, so I use that same thing, but calculated it, I got it as
Oh,
0.0,
yeah, no,
0.2.
no, no. It should be 0.0625 because it's 2, but it's squared. So it will be 1 by 4 times 1 by 4, right? So it is 1 by 16. It should be 0.0625. Now let me go to my code. This is week 8. Okay, so here, what did you put instead of 1 comma 1? It should be 3 comma 3, right? Because it starts from 0. Is that true? Oh, because, oh, right, kx also starts from 0. So it should be 2 comma 2. But x is from 0 to 2 pi, right? So x is from 0 to 2 pi. And this is 0 to 2 pi. 64 points. This will be 0 to 2 pi. N is 64, xy is mesh grid. Function will be 1 plus np dot sin xx square times np of cos yy square, and rest of it should be okay. Let's just run this. Oh, did not import numpy. And it still gives 4.2.
In cos yy, there is a square term over there.
Oh, I write 2. Okay, thank you. It gives 0.0625. So it gives the correct answer.
Yes, that's the reason that I tried your code and I got same answer. But I tried to make by myself, then I got the wrong answer. And like all the questions are not similar like this one.
Mm-hmm.
Every time I can't copy paste your code and do the answers.
Right.
So that the my concern at that time also. First one also I get the wrong answer even.
Mm-hmm.
That is get wrong means two three times I tried and two three times I get the different answer. So
Okay. So
so
I mean,
that's the problem.
so what you can do is after you have see, we are not supposed to help you with the current assignment. We have this strict instruction because it's unfair to the others who are watching this later, right? So we have the instruction not to help you with the current assignment, but after it's gone, you can write to me, you can send your code, and you can ask why it's not working. Or if you want me to do it during the next live session, you can ask me.
So it's a last assignment. It's not this. It's get already ended on 18.
Yeah, this one, right? Week 8. Yeah, that's why I did in front of you. So
Okay.
you can look
Is it
at your code.
allowed?
Yeah, yeah. Previous assignments I can obviously help because it's already submitted, right?
Yeah.
You
I
can
got the
already
answer
see the X.
zero maybe
Which
in
one?
the first one.
In
First
the
one.
first one,
Hmm.
you got 0,
One.
but it's
Zero.
1.
Yeah. In there also I change make the changes as the same one, but I
Mm-hmm.
didn't detect where I get the wrong things over there. Okay. It's really like whole things I have to read it back and then find out small thing.
Yeah, yeah. But
Maybe
yeah, you have to look at it, or if you can't find it, then just send it to me. Okay. Do you have my email?
yes, yes. You share with two, three lecture
Yeah,
previously.
yeah, yeah.
Okay.
So please send the code. Otherwise,
Okay.
yeah, because if I don't have your code, how can I point out what is wrong with it? Right.
Okay. I will. Thank
Okay.
you.
Yeah. But one thing I can tell you is that for this kind of questions, you can do it analytic, right? For example, in this one, C is already given to be 2 speed, and you know that phi of x comma t is phi of x minus ct comma 0. Okay, so let's just do this. So phi of x comma t is phi of x minus ct comma 0, and phi of x comma 0 is given, right? It was what, e to the power minus 32 x minus 2 square, something like this, x minus 1 square. So this is 1. Okay, and we have to do so 5.01 comma 2. which will be phi of 5.01 minus 2 times 2, right? C is equal to 2, comma 0, which is phi of 1.01, comma 0, and phi of 1.01 we can get from this one. It is e to the power minus 32. Instead of x, we have 1.01. So 1.01 minus 1 square, which is e to the power minus 32 into 0.01 whole square. Okay, so it is e to the power minus 32 divided by 100 into 100, 10,000, which is e to the power minus 0.0032. This is correct? Yeah. And this you can plug in calculator, or you can just expand this. It is 1 minus, so e to the power minus x is 1 minus x plus x square by 2 factorial minus x cube by 3, right? So it is 1 minus 0.0032 up to first order, and then you have order of epsilon square, where epsilon is this number. So very approximately it's going to be 0.009968. Okay, so very close to 1. When you round off, it should be 1.00. Okay, so I'm basically telling you how to cheat in such questions when you just have to give MCQ. Okay, that way if your code makes mistake, you can know that there is something wrong.
Okay, okay. Thank
Okay,
you.
sure. Okay. Any other questions? Anyone else? Okay, then let's discuss this week's. So this week was again PDE solvers, but the methods that we used was finite difference. Okay, so and as usual, let's start with idea. Idea. Idea is that you discretize your space, and the equation is of the form del phi by del t is equal to some function of phi itself or its derivatives, right? Del phi del x, del 2 phi del x2, etc. So you start at t is equal to 0 and discretize your system from phi 0, phi 1 to phi I, right? And you have phi n minus 1. And then you say after some time, so t is equal to delta t, you update it. So you again get phi 0, phi 1, but it's at the next iteration, right? So if this was 0th step, this is one step. And how do you get it? So well, you say that updating in phi 1 is this del phi by del t, and that depends on del phi by del x, del 2 phi by del x2, and that is computed using these values. So if you are using central difference, for example, then these two values will tell you this one. Again, this one will be determined by these two or three values. Okay, so this way you get phi, all the phi's at t is equal to 1. Then you go at t is equal to 2. Again, do the same thing. Yeah, dot dot dot. Yes, and these last points are always notorious. So we need to know the periodic boundary condition. What boundary condition is there? So if it is periodic, then after doing everything, you have to write one more sentence that phi n minus 1 is equal to phi 0. If it is absorbing condition, what's the word that he used? Vanishing. Yeah. Then you say, simply state it, right? Phi n minus 1 is 0, phi 0 is 0, etc. And there is another one, which is no flux, which basically is that del phi by del x at boundary is equal to 0. So the slope of phi should be 0. In that case, you write phi 0 is equal to phi 1 and phi n minus 1 is equal to phi n minus 2. Okay. So what happens in periodic boundary condition is that this is determined from this. These two have to be made equal, right? To not draw such long arrows, so we are not actually drawing arrows in computer. What we can do is add two extra ghost points. So these two are extra ghost points. So this is your phi 0, phi 1, etc. to phi n minus 1, and this is like phi minus 1, and this is phi n, right? Which are not your actual points. But then to calculate phi 0, 1, you can use these two, these three, and for this one, you can say it's this one, and at the end, say that phi n is equal to phi 0 and phi minus 1 is equal to phi n minus 1. So it's the same thing, but now what you can do is vectorization, because for every element in this middle section bearing these boundary points, they follow the same rule, right? If it is 3 point central difference, then use 3 points, these 3 points. Then for this one, use these 3 points. So the point itself and two of its neighboring points. So that makes task easier and faster. Okay. So and then we went on to solve some equations. In fact, the same equations which were there last time. So the first was it diffusion or wave? I think, yeah, first was diffusion equation, which is del phi by del x is t times del 2, sorry, this is t, del 2 phi del x2. Did we use t or k? Yeah, professor used k or kappa, right? So kappa determines how fast you are diffusing, right? And for that, uh, well, we said it is d phi by dt, but you cannot just create from PDE to OD without some expense, right? So what is the expense here? Well, you have n equations for n points. So here I itself goes from 0 to n minus 1. Okay. So it's always the case. Whenever you convert PDE to OD, you have multiple equations. And this is kappa. And this has to be estimated. And we have spent 1 week on estimating derivatives, right? So one method which we all of us have seen is this central difference scheme, which is that first calculate derivative forward minus derivative at minus backward and divide by h. Okay, because it's a derivative of derivative, and so this will become, what is forward? It is phi I plus 1 minus phi I divided by h. and this is phi I minus phi I minus 1 divided by h. That is the backward derivative whole divided by h. So I can take h outside, h square in fact. In bracket I get phi I plus 1. From this I get plus phi I minus 1 and minus 2 times minus phi I and minus phi I. So 2 times phi I. Okay. And this can be solved using ODE solver, right? For example, well, simplest is Euler forward. Then the other one is RK2, RK4, etc. We have seen this, right? And the coefficient is this k by h square. Okay. And then you can do stability analysis for each mode. So you write that your solution phi of x comma t is one of the Fourier modes. So e to the power ikx times some function which is just t. So what you are doing is separating. Is it S E or S? I think separate. Separating variables. And then look at how f evolves. Okay. So if f dies, then it's okay when the solution is supposed to die, and otherwise it's erroneous, then you say it's unstable, right? And if you put the solution for Euler forward, this is only for Euler forward, okay? Then you get fn plus 1 is equal to fn times 1 plus 2k delta t divided by h square and cos kh minus 1. And then you ask when does this coefficient become less than 1? Mod of this. So mod of this less than 1, and that gives you a time scale delta t should be less than h square over 4 kappa. Okay, what does this mean? This means that as you decrease h, the grid size, you need finer and finer time resolution as well. In fact, it is h square. So if you make the grid size half of initial, then you need this delta t, the time step, to be 1/4 of the initial one. Okay, and that's why it's difficult and it's expensive computationally to solve PDEs, because if you want very high accuracy, you have to do lots of grid points and then therefore lots of time steps. Okay, so that is that. And earlier we had seen that using spectral method, it is this relation 4h square sp divided by k pi square, and we also know that relation between h forward. So this is finite difference, right? Has to be h spectral divided by 2 pi. This was there in previous lectures. So if you combine all of them, what you get at the end is delta t ft divided by delta t sp is equal to 1 by 32 roughly. Okay. And again, the number 32 itself is not important, but this number is quite small. It's like 3%, right? So what it means is that if you want to use finite difference, you will have to use 3% of the delta t for spectral method. Now using delta t small is bad, right? Because for the same time duration, you need to have more time steps. So it will take longer to run. That's why spectral is better. Alright. And vectorization, I think when we do the code, it will be clear. Let's look at wave equation, which is del phi by del t plus c del phi by del x is equal to 0. And we should know two things. Note one, c is equal to speed written in this form. Okay, if you take it on negative right side, then it becomes negative. And second is what we did earlier. Phi of x comma t is known in terms of initial condition. It is x minus ct divided by 0. So the shift is ct rightwards. Okay, so that's a general thing. So whenever you do some kind of coding and using any method, just check it. Okay, it's a sanity check. So this equation becomes d phi by dt, but again you don't have just one phi, but phi at every point I, and it is minus c del x y phi del x, and this can be estimated. So one is, if when you look forward, it is phi I plus 1 minus phi I divided by h. Other is look backward, phi I plus 1 divided by h. Third is look both ways. So phi I plus 1 minus phi I minus 1 divided by not h but 2h. Okay, because you are looking at I plus 1 minus I minus 1. Okay, so this is third one is the central difference. This is the forward difference. This is backwards difference. And turns out if C is positive, this upstream backward difference upstream is good. With by that I mean it's stable, right? For some delta t, and that delta t is what you would expect is the shift that will happen if delta t is such that the shift is equal to one grid point. So it will be just delta x divided by c. Is this correct? Yeah. So it should be less than this. This delta x is just h. Okay, so h by c. Okay, so in one time step, it should at most shift to one grid point. That's the English. So in one time step, the wave should, what's the better word? Progress or propagate at most by at most one grid point. Okay. Again, I'm not doing the stability analysis entirely because it's there in the lectures. And if you didn't understand, then just let me know. Okay. And then there was Burger equation, right? Which is like the wave equation, rather diffusion equation. So these are, and then in between you have this term. Okay, so these two are like your breads, and this is the patty, chicken or potato, and entire thing is burger. That's why it's called burger equation. Okay, except that it's not. I'm just kidding. It's actually named after a guy called Burgers. But again, idea is that this becomes d phi by dt, duy by dt, and this is just nu times, what was it, ui plus 1 plus ui minus 1 minus 2 ui divided by h square. Okay, and for this one you use, if it is up, if u is positive, use backward difference. So it becomes ui into ui minus ui minus 1. Okay. And if it is negative, then use forward difference. So in fact, let me just write this. So u del xu is approximated as ui times ui minus ui minus 1 divided by h. And in this case, it will be ui times ui plus 1 minus ui divided by h. Okay. And then we did uh, non which two non-linear equations? Yeah, one is Navier-Stokes, which is very inward. So I don't really want to do. If you didn't understand something, then just let me know. And the other one is Schrodinger equation, for which we use leapfrog. Why? Because we want mod psi square to be conserved. So rather integral of mod psi square to conserved. Okay. So any questions? If not, then let's leapfrog to the assignment problems. Let's do this little tiny cute theory problems before jumping to the coding. Okay, so the first is diffusion equation is given, and using Euler forward with finite difference scheme, what should be the stability criterion? Okay, so answers in the chat box. Someone wrote a coding. Yeah, that gives the answer. Okay, answers in the chat box for this one. First one, what's the stability criterion? It's there in the notes. One, yeah, Aparna one, Dr. Khem Thapa one. Yeah, very nice. Well, why one? First of all, common sense. It has to be less than something, right? Delta t has to be less than something. And the other is, we know the factor, right? The factor was this lambda factor was 1 minus 2k delta t by h square. This has to be less than 1, which means this thing at most can be minus 1. So 1 minus 2k delta t divided by h square has to be greater than minus 1. So as you increase this delta t, this number will become more and more negative, but we cannot let it go beyond minus 1. So it has to be greater than minus 1, which just gives us 2k delta t by h square greater than, was it, yeah, 2. That gives us delta t. I made some mistake here. This should be less than, yeah, delta t less than h square by 4k. Okay, then the next one. Again, what's the condition for stability for wave equation? using Euler backwards key, which is the upstream thing, right? उल्टी धारा चीर के जाना. So again, common sense, delta t less has to be less than this. So these two can't be the answer, and this is even dimensionally incorrect. So it has to be this one, and this we saw, right, that in a delta t time, the shift is c times. So shift delta x is c times delta t, and then the delta t should be less than what this shift is. So it becomes delta x by c. Alright, okay. Again, what is the correct relation for stable solution for diffusion equation with spectral method and finite difference using Euler formula? So we just saw it. The factor is 1 over 2, right? And delta t spectral is larger, right? Which is good. We want delta t to be as big as possible without compromising on accuracy or stability. Okay, so the answer is first one. What's the form of error for solving the wave equation using upwind scheme? Delta x and c is given. Okay, so this was done in the class itself. So does anyone remember the answer? Let me show the problem. What's the form of error on solving this equation using upwind scheme? First is delta x times del 4x and del 4 phi by del 4x, then del phi del x, second derivative, third derivative. So if you remember in the class, if you start from a Gaussian profile, then after some time it should ideally be a Gaussian profile with some shifted profile, right? But what it becomes is some spread out thing, something like this. Okay. In fact, I might have it here. So the correct answer is 3. Thanks, Aparna. Do I have the let me just show it on the lecture notes because professor has discussed this. Yeah, wave equation, upwind scheme, and this one. So for central difference, you see this extra Fourier modes, which is due to third derivative, and in upwind, your wave attenuates and spreads out. So that's like diffusion, right? So there is this diffusive term, which is del 2 phi by del x2, the second derivative. Okay, so the correct answer is number 3. Okay, and now we have two coding questions, so we'll look at both of them. First one is a diffusion equation, and everything is given. The box is 0 to 2 pi, grid points are given, and find the maximum value of phi of x at t comma at x at t is equal to 1. So this is the final time point, and we have to use periodic boundary condition, which means we have to do psi n minus 1 is equal to psi 0 every time. Okay, and initial profile is this one. So how does it look? It's a Gaussian. Where is its mean? its mean is at x is equal to pi. Okay, and what's the standard deviation? The standard deviation is e to the power minus x minus mean square divided by 2 sigma square. So if you compare both of this, sigma square is 1 by 4, so sigma is 1 by 2. So this width is roughly 2 times standard deviation, so around 1. So it is centered at pi and the width of the peak is order of 1. And we have to find the function at t is equal to 1. Okay, so what will happen with time is that this peak stays at wherever it is, but it diffuses out. So it becomes something like this. And then we have to find the maximum. So we know that maximum stays, the maxima does not change the point. So it is at pi initially, right? The mean is pi, so it will stay at pi. So we have to find the value of phi at time t is equal to 1 at x is equal to pi. Okay, delta t is given and we have to use RK2. Okay, and diffusion constant is not given, but this there is nothing here, so it's 1. Okay, so let's start coding. First, let's write down all the parameters. Grid points was 64, and then length was 2 pi, 2 times np dot pi, h is L by n. This is the grid size, and x will be from 0 to L, right? Because it is from 0 to 2 pi, not minus pi to pi. So 0 to L, and we can do this comma endpoint is equal to false, or we can do n plus 1 and then just take remove the last element. So we are starting from 0 to up to minus 1 point. So the last point is not considered. Okay. T final is equal to 1. Dt is given to be 0.01. The diffusion constant K is 1. Okay. And the initial profile, init profile is np dot exponential of minus 2 x minus pi square. Okay, this Gaussian profile. And then we have to define f, which will be evolved. Okay, so how long should we make it? Well, it has endpoints, right? So it should be np dot zeros of n, but we want two ghost points outside. So we say it's n plus 2. Okay, and initially f from 1 to minus 1, this is correct. So starting from 1, so omit the 0, 1 and go only up to second last element. So minus 1, that is your initial profile. And the endpoints we define f of 0 is equal to f of n, which is minus 2, right? Or it should be minus 1. It should be init profile of minus 1, which is f of minus 2. But let me just write init profile of minus 1. Okay, so the last point of the initial profile is the first ghost point, and the last ghost point is going to be the first point of the initial profile. Okay, and we start with t is equal to 0 as usual, then use while loop. You can also use for loop like professor does. Okay, in that case you have to specify number of time steps in advance, which will be just int of t final divided by dt. Okay, But let's stick to what we have been doing. While loop, while t is less than t final. Uh, I don't know why it's saying that. We have to use arc2, right? Which means first we define the middle f, which is not the full form of middle finger, but function at the middle point. And this is there in the notes, right? So I'm just copying. 1 to n plus 1 is going to be some factor. He said it's prefactor times the second derivative. And how do we estimate this? Well, it's f of 0 to n. So this is the left neighbor for each element. Okay, so we are doing the vectorization. Then the f of right neighbor, which will be from 2 to n plus 2 and minus 2 times f of itself. So 1 to n. So 1 to n is the real space array, and 0 and the last element is the those are the ghost points. Okay, and this has to be added to itself, right? So f of 1 to n plus prefactor. Oh, I forgot to define the prefactor. Prefactor, as we saw, was k times dt divided by h square. Have we defined dt? Yes. So we are going only up to middle point. So it will be prefactor divided by 2. Okay, this is RK2, and we have to write one thing, which is what happens at boundary, which is important, right? So f mid of 0 is equal to f mid at n, and f mid at n plus 1 is going to be f mid of 1. So the last point, which is the ghost point, is equal to f of 1, which is the first point of initial profile. Okay, and then we do the second step, which is the real thing. So f from 1 to n plus 1. This will also be n plus 1, right? It's going to be f of from 1 to n plus 1 plus the update term, and this time it will be prefactor times the same thing. But instead of f, we will use f mid, right? And then t plus is equal to, okay, we have to do this thing, boundary condition. So f of 0 is equal to f of minus 1, f of n rather, and f of last element is going to be f of 1. Okay, and t plus is equal to dt, and we want to find the maximum value of f rounded up to 4 decimal points. So we have rounded up. So np dot round this thing up to 4 points. Let's run this. What's the issue? Have I defined f mid? Oh, I haven't defined f mid. So f mid is also going to be zeros of n plus 2. Okay. It's saying operands could not be broadcast with shape 64 and 63. 0 to n, 2 to n plus 2, 1 to n. Does anyone see any mistake? Let me just print length of, so np dot size of f 66, which is correct, and f mid that is also 66. What's the issue? Oh, this is 1 to n plus 1. Right, of course. Okay, so the length of this should be n. So n plus 1 minus 1 should be n. This is n. This is n. This is n. This was n minus 1, the difference. So it should be n. Okay, and the same thing here. Yeah, here I wrote correctly, I think. Let's run it. And it gives 0.3336, which seems to be the correct answer. Yeah, this one it's 0.3335. I don't really know why that happens, but I'll tell you one thing. In professor's notes also, you have the code, right? It goes up to n steps plus 2. So if you look at this code, this is basically what I did, right? Same thing. So in for range, it goes from up to n steps plus 2. So up to n steps plus 1, right? That would be the last one. But you have to go only n steps. So it looks like they are going one step extra. And if we do that here, which is tantamount to adding dt here, so we can go one step extra. Then we get the exit 3335. But I really don't understand why we should add dt here, right? Because in the last step, anyway, we are adding dt. And only after that, this will be executed, right? So anyways, the answer is very close to 0.333, and there is only one option, which is the first one. Okay, second one. Again, first thing, c is equal to 1.5, and the grid point and everything is given, and x is at 3.48. Initial profile again Gaussian. So what should we do first? Calculate analytically. So we want psi at 3.48. This is your x at t is equal to 1, which is psi of 3.48 minus c, which is 1.5 into 1 comma 0, right? So this will be psi of 3.48 minus 1.5, which will be 1.98. 3.5 minus 1.5 is 2, and then we take out 0.02 here, 0, which will be exponential minus 32. Instead of x, we have 1.98 minus 2 square. Okay, so e to the power minus 32 times 0.02 square. So it is e to the power minus 32 times 4 divided by 10,000. And you can do the same thing as I did earlier, or you can be slightly smarter and get a calculator on your phone and just calculate, but let's do it. So e to the power minus, it will be 0.032 times 4 will be 128. So 0, 1, 2, 8, 1, 2, 3, 4. Yeah, which will be 1 minus this thing, right? So 0.9872 probably. Yeah. Okay, so correct answer should be around this one. This is also approximate, right? The exact answer is this one, whatever it turns out to be, and which is this. So this should be our answer. Let's make it star. Now let's see. Okay, I can copy paste. The question is, should I? So I can copy paste from this one, but if we get an error, then we are screwed. So let's not copy paste. If you have any questions, just ask. Okay, so the first thing, there is one confusion. Initially, it says n is equal to 512 grid points, blah blah blah. Then at the end, note and choose n is equal to 500. So we don't really know to choose. We might get slightly different answer based on what we get. So let's start with n is equal to 512, and L is the same thing, 0 to 25 feet. In fact, let me just copy paste it. H will be L by n. X is from 0 to 2 pi. Same thing. T final is 1. Dt is 0.001. K, instead of K we have C, the speed, which is 1.5. I don't know what this does, but yeah, C is this. Initial profile is np dot exponent minus 32 times x minus 2 square. So this is 32 and x minus 2 square. F is this, whole thing is same. This is a general thing. Yeah, t is equal to 0. This prefactor will of course be different. It will be minus c times, what was it? So it depends on which scheme we use. It's given to be central difference. Okay, so it's this thing. So prefactor will be 1 by 2h times minus c and delta t. So minus c times dt divided by 2h. Rest of it should be same. It's RK2, right? Yeah, RK2 method. And other things should not be changed. Right, so let's run this. Of course, we have to find it at some weird point, 3.48. That will do. Okay, it gives some answer. But what we want is, first we want to find where 3.48 is. So we write np dot where x is equal to 3.48. But x may not be exactly 3.48, right? So we say np dot round of x rounded up to 2 points. That should be 3.48. And this should be the index where function has to be evaluated. So I is equal to np dot where. Okay, and this does not give an index. In fact, it gives a tuple with the first array being the array of index. So we want the first element because it might have multiple elements. We just want the first element. And if there are no elements, then it will give an error. Okay, and then we want to print np dot round fi comma 2. Yeah, function at that point rounded up to 2 points. So let's run this, and there is an error. And it's important to be able to understand the errors, right? What it says is index 0 is out of bounds for x is 0 with size 0. So there is an error with size 0, and it does not have, and because it's size 0, it does not have any element. So index 0 is not there, right? And we are calling index 0. So either this thing does not have any element, which we know can't be true because it's a tuple. So it can have an empty array, which is what is there because this array is empty. So it does not have first element. This means that we did something wrong. Oh, we did not choose n is equal to this. So we had to choose n is equal to 500 or 512. We'll see. Yeah. Oh, why is it giving such high numbers? Oh, right. I have to change this. This is for second derivative. For first derivative, it's just f to the right number minus f to the left number divided by 2h, which is already there in the prefactor. Okay, and same thing here. So this won't be there, and this will be minus. It gives 0, 0.0, which is also incorrect. Oh, it should be right minus left, right? So it should be this. So the wave went leftwards, so there was nothing at the center. Yeah, now it gives 0.98, which was one of the options, right? Okay, so answer is 0.98, which is what we got using pen and paper also. This is not exact answer, okay? because we did Taylor expansion nonetheless. So we can actually write down the actual answer. So let's not round it off. Let's say up to 6 decimal and then print the actual answer, which was np.exp. So same function as initial, and instead of x I have 3.48 minus c times t final. Yeah, 0.987281 and this is 0.977, so pretty accurate but not exact as usual. Okay, any questions? Okay, so just to revise, first we write all the parameters, define the x as linspace from 0 to L, and then give the initial profile. Then we write down the function, so the array of function initially, right? And we add two extra ghost points. Then we define another array, which is fmid because we are doing rk2. Okay, and then we respect the boundary conditions, then do the rk2. And while doing that, first we write the middle part of f because first and last points are the ghost points. Do it usually. Then remember that there is boundary condition and do the same thing again because it's rk2. So first you multiply by prefactor by 2 to get this middle function and then use it to update your f. Okay. Okay. Well, we can do one thing. We can plot like we have done in past. So let's plot plt.plot first the initial function, which is how did we define init profile, and then plot f, but only from 1 to n, right? Because others are ghost points. So 1 to n means we have to write 1 to n plus 1. Last point is never considered. Okay, you can in fact label it. This is at t is equal to 1 and computed. This is initial and plt.legends. Legend. There are some mistakes that I keep on doing. Okay, so we have a wave. This is the initial one and it was moving with some positive speed, so it came here. Okay, and in fact we can check, we can use the analytical solution, which is this, right? So just plt.plot x comma this thing and label t is equal to 1 exact. It gives x label and y label as well. And instead of 3.48 we have the entire x array. Okay, and then we see that they almost coincide. We should make this dashed line. Okay, so we see that they coincide, they collapse onto each other, so it's pretty exact. We can do the same thing with Gaussian, the diffusion equation also, right? And let's do it just for fun. So plt dot plot. In fact, it's the same thing, right? So I can copy paste. Except this will be this we don't know. Okay, I need to run this first. Okay, so initially it is like this. The large peak centered around 3, 3.14, right? Slowly it diffuses out, so it spreads, so the peak decreases and the spread increases. Alright. And by the way, we can do one more thing, which is the analytical solution, which I've already done. And I'm not going to use pen and paper because it's very long and does not serve us that much of a purpose. But I'll show you for those who are interested. This is a PDF that I found online. So it is exactly like this. You have an initial Gaussian profile and then it is diffusing. So how do you solve it? Using Fourier transform, right? So first you find the Fourier coefficient at time 0, so the initial coefficient, and then you realize it's multiplying by e to the power minus ikx, right? And then integrating. So then you complete this square, full square, and whatever that remains can be taken out because it's not a function of x. So you get e to the power minus k square sigma square, and whatever remains it's a complete square with a negative sign. And then you can argue that that is equal to square root of pi because that's a usual Gaussian integrate. Since this is a math course, so they go on to prove it using Cauchy integral formula. So you have to respect certain condition for this function, etc. But since we are doing physics, we really don't need it. So we get initial Fourier coefficient, which are also Gaussian, right? You see this as a function of k is e to the power minus k square sigma square by 2, which is a basic fact in Fourier transform. Gaussian is the only function which is a Fourier transform of itself. Okay, and that has one consequence, by the way, in physics, which is in the Heisenberg inequality. So Heisenberg inequality does not come from quantum mechanics. In fact, it does not come from Schrodinger equation. It's just a statement on Fourier transform. And then you can actually prove that the equality holds only when your profile is Gaussian, because then you have Gaussian on both the sides. Okay, so that's just some side thing. And then you can, you know the equation for the Fourier transform. So that is an ODE which you can integrate. Then you get finally this expression. Okay, which is also Gaussian. So if you look at this, this is a Gaussian e to the power minus x square by something, and this something is the standard deviation. If you look at the standard deviation, it is 4 dt plus sigma square by 2. This was the original standard deviation. So what is happening is that it's spreading out, right? And the spread is dt. So the standard deviation itself spreads by dt. So if you look at the width, which is just sigma, that spreads as square root of t. So that's a basic fact for diffusion equation, that this spreading occurs at speed which is square root of t. Okay, so it slows down, slows down. In fact, you can plot standard deviation as a function of t and you see it to be square root of t, or you can plot sigma square versus t and it becomes a straight line. Okay, if you if we have time at the end, if you want me to do, we can do it. All right, and for this wave, we knew the exact solution. So yeah, we can write exact solution here also, which I'm copy pasting from that PDF. I'll share that PDF on the Google Drive if you want to take a look. So first I define the initial sigma square, which was 1 by 4. And the new solution is this y is np dot sqrt of sigma square divided by 2 times something, and that something is k times t, the diffusion constant times t. So t final and plus the original sigma square by 2. And this entire thing multiplied by np dot exponential of minus, yeah, I think is this correct? Let's see. Minus x minus pi square divided by 4kt final plus sigma square by 2. It's correct. So let's plot x versus y. Let's see. Yeah. So the orange one is the computed one and green is the exact solution. So it pretty much coincides, pretty much equal, except at the boundary, which we can understand, right? Because we used periodic boundary condition, which means we did not let stuff run out of this box. Whenever it ran out, it came from here. So originally in the equation itself, it was diffusing, it was going out of the box. All of those got accumulated at the end. Yes, so at both the ends, we have some deviation, and that deviation is positive. All right. So that is expected. Okay. Yeah, so I think we are basically done. Yeah, just I wanted to show in 2D what happens. So since I am lazy, I just gave it to the AI, and then of course I checked whether it's correct, but I gave this prompt 2D diffusion using finite difference at different times. So it gave out a nice code. Let's look at the code first. It's pretty similar to what we did, but you have to use mesh grid now because u is going to be function of x and y both, and then it just uses the central difference scheme just like us, but then you have central difference in both the directions. So it is I plus 1 plus I minus 1 minus 2 times ui, that is in x direction, and same thing you do in y direction, which is j. So now you have two loops running for I and j. Okay, and we haven't done vectorization here, and the boundary condition is taken to be periodic, and then give the parameter and basically solve. The initial condition is some Gaussian profile, so np dot exponential, and this is mean in x direction, which is 2. So it is centered at x is equal to 2 and y is equal to 2, and this is your variance, right? 2 sigma square. So it is centered at 2 comma 2, and so let's look at it. So initially it's where there is a high peak and spread is very less, and slowly it diffuses in all the directions, right? So it diffuses out. So this is at different time. This is at 0, then 0.2, then 0.4, 0.6. All right. And if you actually look at the spread in this case, it will also be proportional to t. Just the sorry, proportional to square root of t. Just the coefficient will be different. It will be square root of 4D, I think, instead of 2D. Okay, so that was something that I wanted to show. Anything else that you want me to discuss? Okay, then I think this assignment is also easy in that the questions are similar to what we have done in this session. So I think you should be able to do it. If not, just give it a try. And just one tip that check with the analytical solution just to see if you are not making any silly mistakes. And if you can't do it, send it to me or we can discuss in the next session. Okay. Any questions? All right, then bye bye everyone. Yes, Narhariji, do you have any question?
No, no, sir. Everything is good, sir.
Okay, perfect. Thank you very
Thank you,
much.
sir.
Yeah, yeah. Okay, let's meet next week. I think it's going to be easy. Next week is going to be very easy. So
Okay,
it will
okay,
be fun.
okay.
Let's see. Chalo. Let's meet next week. Bye bye everyone.
Thank you. Bye.
Yeah.